Welcome to the Deep Dive. Today we're looking at a really profound shift happening in AI. It's moving beyond just generating stuff, content like text or images.
Right.
We're talking about systems that can actually take action. And that's fundamentally redefining automation, especially in complex areas like, well, software engineering.
It's a huge leap.
Yeah. I mean, imagine an AI, right? It doesn't just spit out a block of code. It takes that code, tries to compile it, looks at the error message if it fails, and then, this is the key part, entirely on its own, decides how to fix it.
Autonomously.
Exactly. That's the leap into agentic AI we're diving into today.
Yeah, and our deep dive today is squarely focused on agentic AI in software development evolution. And like you said, it's not just about coding faster, though that's part of it.
Right.
It's a fundamental rethink of how software gets built, and maybe even what it means to be a software engineer going forward.
So what are we covering?
So we'll dig into the core ideas, the foundational principles. We'll trace its history a bit, see where it came from, then really look at how it's transforming the software development lifecycle, the SDLC.
Okay.
And we'll survey the tools, because there's a whole ecosystem popping up. Crucially, we'll also talk about the changing human roles and, the big challenges around trust and governance. That's key.
Absolutely. So our mission, as always, is to take this stack of sources you've shared, articles, research papers, expert notes, and really pull out the core insights, the nuggets of knowledge. Give you a shortcut to getting up to speed on this revolution.
Let's do it.
Okay, let's unpack this.
Yeah.
Understanding agentic AI. The leap from generation to action. So let's start right at the beginning.
Yeah.
For a while now, the big buzz in AI has been generative models, right? Especially large language models, LLMs.
Yep, they've dominated the conversation.
And they're amazing at creating content, text, images, code. They learn patterns from huge data sets and replicate them. But fundamentally, they're reactive.
Reactive is the key word there. They need a prompt. They produce an output in response to your command.
Like a super smart autocomplete, maybe?
Mm-hmm.
But it still waits for you to tell it what to do next.
Exactly. And that's where agentic AI takes this massive conceptual and architectural leap. It's designed to be action-oriented.
Action-oriented, meaning?
Meaning these systems aren't just built to create, but to do. An agentic system is essentially an autonomous entity. It can make its own decisions, take actions independently, all aimed at hitting specific goals, often complex ones, and ideally with minimal human handholding.
Okay, so back to that code example.
Yeah.
Generative AI writes the code block.
Right. But the agentic system takes that block, tries to compile it, maybe it fails, it analyzes the error message, and then autonomously figures out, okay, how do I fix this? It then tries again.
That closes a big gap, doesn't it? The so-called last mile problem.
Precisely. An LLM could write brilliant code, theoretically, but it couldn't actually check if it worked. It couldn't interact with the compiler or the runtime environment. Agentic AI bridges that gap. It gives the LM the ability to use external tools, get real-world feedback like that compiler error, and ground its reasoning in things that actually happen.
Which makes it way more practical for something like software development.
Infinitely more practical, more reliable.
So it's about taking initiative, seeing things through. What are the defining characteristics of this agency? What makes an AI agentic?
Good question. There are really 4 core characteristics that define it. First, and probably the biggest differentiator, is autonomy.
Okay.
It's not just doing things fast, it's taking initiative, making decisions without needing constant human oversight. It really changes who's in charge,
Yeah, I see. What's next?
Second, goal-oriented behavior. Agents are built to work towards specific objectives. You give it a high-level goal, like build me a login page, and it can break that down into smaller steps, create the UI, set up the database check, handle errors, and execute them.
Okay, so it plans.
It plans. Third is adaptability and learning. These aren't static systems. They learn from data, from their interactions, from the outcomes of their actions. They get better over time.
So something goes wrong.
They can often backtrack, reflect, figure out what went wrong, and correct course. That makes them much more resilient than, say, a simple script that just fails if something unexpected happens.
Makes sense. And the last one?
Finally, reasoning. This is the cognitive bit. Using logic, context, information to draw conclusions, solve problems, evaluate different paths forward. It's how they decide which action to take next.
That sounds incredibly sophisticated. Is it just a matter of having a bigger, smarter LLM under the hood, or is the architecture itself different?
It's definitely more than just a bigger LLM. That's key. The agentic capabilities come from a more complex modular architecture. And interestingly, it often mirrors principles from cognitive science.
Oh, so.
Think of the agent as like a program or a wrapper that uses an LLM or maybe multiple LLMs as its reasoning engine, but it adds other crucial pieces. The typical flow is this cyclical loop. Perceive, reason, plan, act, learn.
Perceive, reason, plan, act, learn. Okay.
And that cycle deliberately parallels how we think, right?
Yeah.
We perceive the world, we process information, we make a plan, we act, and we learn from what happens.
That's fascinating. It's almost biomimicry in software.
It kind of is. And it suggests that future progress might not just be about scaling up the LLMs, but about making these other modules, memory, planning, learning more sophisticated, maybe drawing more inspiration from neuroscience.
That's a really powerful way to think about it. So let's break down that loop. What are the actual components doing to perceiving, reasoning, planning, acting, and learning?
Absolutely. So at the heart, you've got the LLM as a reasoning engine. That's the core brain, handling the natural language understanding, the context processing, the logical inference.
The smart part.
The smart part, but it needs to know what's going on now, right? That's perception.
Yeah.
This module gathers data from the environment. It could be APIs, databases, user input, sensor data if it's a physical agent. It makes sure decisions are based on the current state, not just old training data.
Right. It needs situational awareness.
Exactly. Then memory. This is crucial for context and learning. Agents often have different kinds. Short-term memory for the current conversation or task, long-term memory for historical knowledge, maybe episodic memory for specific past interactions. This helps maintain consistency.
Okay, so perceive, remember. Then it has to think and do something.
Right. That brings us to planning and reasoning. It takes the perceived data, uses its reasoning engine to interpret intent, spot patterns, understand the goal, and then develops a plan. Often this means breaking down a big goal into smaller, executable steps. It might use algorithms to weigh different options.
And then the action part. How does it actually do things?
That's action and tool use. This is what really gives agents their power. It executes the plan by interacting with external systems using tools.
Tools? Like what?
Could be anything, really. Calling an API, running a command line script, querying a database, interacting with a web browser, even controlling a robot arm. This ability to use tools is the bridge from thinking to doing. It's what separates it from a passive model.
Got it. And final piece, learning.
Learning and self-refinement. After acting, the agent looks at the outcome. Did the API call succeed? Did the code compile? It gets feedback from the environment and uses that feedback to refine its strategies for next time. This self-correction loop is vital for improving and handling errors.
That really clarifies the different levels of AI we hear about, because agentic AI sounds like it's at the top of a hierarchy. So much confusion out there.
Absolutely. AI gets thrown around for everything. A clear taxonomy helps. So at the bottom, maybe you have simple bots.
Like chatbots for FAQs.
Exactly. Rule-based, reactive, handle very simple tasks, almost no autonomy or learning.
Okay. Level up.
Then you have AI assistants. Think Siri, early Google Assistant. They understand natural language better, can do more complex tasks, but still mostly reactive. They wait for your command, often need confirmation, limited autonomy.
Right. And the generative AI we started with.
Yep, generative AI, GPT, DLE. Amazing at creating content, trained on massive data sets, but fundamentally passive. They need a prompt for every single action. They can't interact with the world on their own or check their own work, really.
And that brings us to the top.
Agentic AI, proactive, goal-oriented, handles complex, multi-step tasks, makes independent decisions, learns continuously. Crucially, it can generate its own next steps or prompts in a sequence to achieve a high-level goal without you needing to guide every single step.
That's the leap from passive creation to active autonomous doing.
Precisely. And for you, the listener, understanding that distinction is key. It highlights both the potential and the challenges we need to discuss.
Okay, that really maps out the landscape. Now, if one agent can do all that, what about putting multiple agents together on a job? Is that happening?
Oh, definitely. That's a major frontier. Just like complex software projects need teams of humans with different skills, many problems are too big or too multifaceted for one AI agent. That's led to multi-agent systems, or MAS.
MAS, okay.
It's basically a framework for getting multiple AI agents, often specialized ones, to collaborate effectively.
How does that usually work? Is there a boss agent?
Often, yeah. A typical setup has a central orchestrator. You might call it a meta agent or a supervisor. It gets the main goal, breaks it down, and then delegates tasks to a committee or crew of specialized agents.
Like an agile team. Project manager assigns tasks to the dev, the tester, the designer.
Exactly like that. It's a great analogy. And these MAS architectures have some key characteristics. They're modular, you can add new agents with new skills easily. They're scalable, you can handle bigger problems by adding more agents. And they need interoperability the agents have to communicate smoothly, maybe through shared memory or standard protocols.
So what are the big wins of using a team of agents versus just one super agent?
Several big advantages. One is robustness and accuracy. Just like peer review in code, one agent's work can be checked or validated by another.
Built-in quality control.
Right. Another is fault tolerance. If one agent fails or gets stuck, the whole system doesn't necessarily grind to a halt. Others might be able to take over its task.
Makes sense. Redundancy.
And finally, you can get divergent thinking. Different agents might approach a problem from different angles, leading to more creative or comprehensive solutions than a single agent might find. Sophisticated MAS frameworks are really critical for tackling the really big, ambitious challenges, especially in software engineering. It's how we get from individual AI smarts to collective AI intelligence. 2, the historical journey, automating software development.
Okay, so this idea of agentic AI, it feels very cutting edge, very futuristic. But it's not like it appeared out of nowhere, right? It builds on a long history.
Absolutely not out of nowhere. You're right. It's really the latest chapter in this decades-long quest within computer science and software engineering. The goal has always been, in a way, to raise the level of abstraction. Meaning making it easier for humans to tell computers what to do, automating away the tedious, complex parts of programming.
So going way back, programming used to be incredibly manual, didn't it? Machine instructions, punch cards.
Oh, yeah. In the very early days, like the 1940s, programming meant figuring out individual machine instructions, managing memory locations by hand, physically wiring plug boards, or punching holes in paper tape. The very first notion of automatic programming was literally just automating the punching of those tapes or cards.
Wow. Okay, so just mechanical automation.
Pretty much. But the definition evolved quickly. By the 1950s, with languages like Fortran and LGOL, automatic programming meant translating these higher-level, more human-readable languages into machine code.
The first compilers.
Exactly. And interestingly, one of the earliest compilers was actually client autocode. Compilers were a massive step in automation. They hid the messy details of the hardware.
I love that Parnas quote you shared. Automatic programming has always been a euphemism for programming in a higher-level language than was then available.
It's brilliant, isn't it? It perfectly captures that relentless drive towards higher abstraction, automating away the complexity layer by layer. It's been the constant theme.
But as software got bigger, that wasn't enough. You had the software crisis in the late 60s, right? Projects failing left and right.
Yeah, that was a wake-up call. Systems were becoming too complex for the ad hoc methods of the time. Projects were late, way over budget, unreliable. It led to the birth of software engineering as a formal discipline.
Trying to bring some engineering rigor to it.
Exactly. You saw the rise of structured methodologies, things like SRAM, SADT, trying to impose process and discipline. And the first computer-aided software engineering or CASE tools emerged.
What did those CASE tools do?
Early ones helped with editing, compiling, basic debugging. The bigger dream, though, was formal models describe the software formally and then automatically generate the implementation. But these formal methods were often too heavyweight, too difficult to use in practice for large systems.
And that dream kind of evolved into things like UML and model-driven engineering later on.
Precisely. In the 90s, MDE and UML aimed for that goal again. Design software visually at a high level and automatically generate the code. It was a powerful vision, but the early code generation tools often produced clunky code or couldn't handle the full complexity, so a lot of manual work remained.
So lots of attempts, gradual progress. Now, in parallel to all this software engineering stuff, AI was developing its own approaches, wasn't it? Thinking about reasoning.
Yes, that's a crucial parallel track. While software engineering focused on process and structure, AI was exploring automated reasoning. The big success story there in the 70s and 80s was expert systems.
Right, trying to capture human expert knowledge.
Exactly. You'd codify the knowledge of, say, a medical diagnostician or a geologist into a knowledge base, and an inference engine would use rules to apply that knowledge, mimicking how the human expert would reason.
Were these related to the agentic AI we see today?
Conceptually, yes. They were distinct technologically, but they were critical precursors. They were the first real demonstration that machines could perform automated reasoning for non-trivial problems. That was a huge conceptual hurdle to overcome.
But they also led to the AI winter, didn't they? The hype got ahead of reality.
It did. There was
Yeah.
massive hype in the 80s. Expert systems were going to revolutionize everything, but they hit limitations. They were often brittle. They broke easily if faced with a situation outside their narrow expertise. They were expensive to build and maintain. The knowledge acquisition was a bottleneck.
The funding dried up.
Yeah, the hype bubble burst, leading to a significant downturn in AI funding and interest, the AI winter. And this is a really important cautionary tale for today.
How so?
Because the current excitement around agentic AI feels very similar. Grand promises of automation. For agentic AI to avoid the same fate, it has to overcome similar challenges. Brittleness, scalability, cost, and maybe most importantly, the issue of trust. We have to learn from those past boom and bust cycles.
That's a critical point. Okay, so moving closer to the present, the most direct ancestor of agentic AI seems to be the AI tools that started augmenting developers, right?
Yes.
Like advanced code completion.
Yes, exactly. This augmentation phase is the immediate precursor. It started modestly with IDE features like syntax highlighting, basic code completion. Think Microsoft's IntelliSense. Helpful but small boosts.
But then came the LLMs trained on code.
That was the game changer. Models like OpenAI's Codex, trained on billions of lines of code. They powered tools like GitHub Copilot. Suddenly, the AI wasn't just suggesting the next word. It was suggesting entire functions, complex blocks of code based on comments or the surrounding context.
The AI pair programmer.
That's what it felt like. It dramatically accelerated coding, reduced boilerplate, a huge step in augmentation.
But still augmentation, right? The developer was ultimately in charge.
Absolutely. Even Copilot, as powerful as it is, remained reactive and augmentative. The developer had to take the suggestion, integrate it, test it, debug it, manage the whole process. The AI wasn't running the show.
And that limitation, that inability of the AI to handle the whole workflow autonomously,
Created the clear need, the clear opportunity for the next step, for agentic systems that could take ownership of that entire lifecycle. Implement, test, debug, maybe even deploy. Moving AI from assistant to active participant. That's the journey that got us here. 3, the Agentic Software Development Lifecycle, A-SDLC. A new paradigm.
Okay, this is where things get really, really interesting. Because agentic AI isn't just tweaking the existing process. It sounds like it's forging a fundamentally new way to build software, a new life cycle.
That's exactly right. We're talking about an emerging Agentic Software Development Lifecycle, or A-SDLC. It's a paradigm shift beyond traditional human-centric methods like waterfall, agile, even DevOps as we know it.
How does it compare to, say, Agile? Agile was all about iteration and human collaboration.
Right. Waterfall was rigid, sequential. Agile broke that with iterative cycles, human feedback loops, but it still operated at human speed. The ASDLC is the next big jump. It's agent-driven, iterative, with automation baked into its core.
Agent-driven. So taking Agile principles and putting them on steroids, basically.
You could say that. It accelerates core Agile ideas, rapid iteration, continuous feedback to machine speed. It does this by removing the human bottleneck from the execution loop. An Agile sprint might be weeks. An agentic cycle code change, test, analyze, refine could happen in minutes or hours.
Wow. And it can handle more complex stuff than traditional automation scripts.
Yes, that's key. Traditional scripts are deterministic. They do what they're told. Agents, because of their reasoning and planning capabilities, can tackle more open-ended problems, complex, multi-step processes that you couldn't easily script. This also leads to what we might call agentic DevOps.
The agentic DevOps. So AI agents participating in the CI/CD pipeline.
Actively participating, autonomously. It's far beyond just running scripts. An agent might decide which tests are most relevant to run based on a code change. It could analyze the failures, maybe even attempt a fix before alerting a human.
Okay, that's a different level.
It manages deployments, monitors production, performs initial incident response. It's intelligent automation woven throughout the entire life cycle.
So let's walk through that life cycle phase by phase. How does the ASDLC transform each traditional stage? Let's start at the beginning, requirements and analysis.
Okay. Here, you could have requirements analysis agents. Imagine feeding them meeting transcripts, emails, documents. They use NLP to extract, classify, and formalize these into structured user stories or specifications.
So automating that tedious requirements gathering.
And more. They could identify inconsistencies or ambiguities between requirements, flag them for human review, and even build a knowledge graph linking business goals to specific features.
Huge potential time saver there.
Yeah.
Okay, what about design and architecture?
Once requirements are clearer, architecture design agents could step in. Based on the specs, they might generate architectural diagrams, suggest relevant design patterns, microservices, event-driven, etc., and even perform automated trade-off analysis.
Trade-off analysis, like performance versus cost.
Exactly. Performance, scalability, cost, security. They could present different architectural options with pros and cons for a human architect to review and make the final call.
Okay, now the core. Implementation and refactoring. This must be a sweet spot.
It is. Code generation agents take the design and specs and translate them into actual code, potentially in multiple languages, while adhering to coding standards. But maybe even more impactful is continuous autonomous refactoring.
Dealing with technical debt automatically.
Yes. Agents could constantly scan the code base, identify tech debt, inefficient patterns, areas needing optimization, and then execute the refactoring autonomously. Think about large-scale migrations, like moving from an old language like COBOL to Java. Agents could drastically lower the cost and risk of that.
That alone would be a game changer for so many organizations. Okay, testing and quality assurance. This is often a major bottleneck.
And this is where the A-SDLC offers a massive shift. Traditionally, QA happens after code is written. Here, quality becomes an intrinsic in-process thing. Testing agents generate comprehensive test suites unit integration end-to-end directly from the requirements, often in parallel with code generation.
So the feedback loop shrinks dramatically.
To almost instantaneous. And here's where it gets really interesting. The concept of self-healing test automation.
Self-healing. What does that mean?
Okay, picture this. A UI element changes, maybe a button moves. In traditional test automation, that breaks the test script. Someone has to manually go in and fix it. It's a huge maintenance burden.
Yep, been there.
A self-healing agent could analyze the failure, understand the underlying business function is the same, and autonomously adapt the test script to work with the new UI.
Wow, that tackles a massive pain point in test automation.
It really does. Huge cost savings potential there. Finally, deployment and operations, the agentic DevOps part.
Right. How do agents change CI/CD in production?
They bring more intelligence to the pipeline. They can generate and manage deployment configurations, Docker files, Kubernetes manifests. They can dynamically optimize deployment strategies like canary or blue-green releases based on real-time monitoring. They automate rollbacks if things go wrong.
And once it's live,
They act like tireless operations engineers, monitoring system health, logs, performance, performing root cause analysis for incidents, self-healing common problems, and providing detailed context when they do need to escalate to a human. It's a continuous loop.
so the overall impact isn't just speed. It fundamentally changes the economics of building and maintaining software.
Absolutely. The A-SDLC drastically reduces the cost and risk associated with making changes and maintaining systems over time.
How specifically does it achieve that economic shift?
One key pattern is iterative, multi-stage prototyping. Instead of trying to generate complex production-ready kind straight away, which is hard even for good LLMs, an agent might first generate a functional prototype in a simpler, high-level language like Python. This lets you validate the core logic and requirements quickly and cheaply with stakeholders. Changes are easy at this stage.
Get the core functionality right first.
Exactly. Only after that prototype is validated does another specialized agent rewrite the relevant parts into a high-performance language like Rust or Go or C++ for production. This minimizes expensive rework on the really complex optimized code.
That makes so much sense. De-risks the process massively.
And the other big economic lever is that continuous automated refactoring we talked about. It changes the whole game for technical debt. Instead of debt piling up until you need a massive, costly, risky refactoring project.
Which often gets deferred forever.
Right. Agents can manage it proactively, incrementally, keeping the code base cleaner, more modern, easier to change over time.
Are we seeing actual proof of this?
Yeah.
Quantifiable gains.
Yes, we are. Early studies and reports are showing significant numbers. Infosys, for example, reported things like 80–90% improvement in generating database code, 60–70% for APIs and microservices.
Wow.
Tasks that took developers days or weeks, like creating a full end-to-end test suite or upgrading all application dependencies, were being done by agents in like 30 to 45 minutes.
Days or weeks down to under an hour.
That's the kind of step change we're talking about. An e-commerce case study showed a 95% reduction in test maintenance effort thanks to those self-healing tests. It's not incremental improvement, it's a leap in velocity and efficiency. 4. The modern agentic AI toolchain, an ecosystem survey.
Okay, so this A-SDLC isn't just theory. Tools are being built right now to enable it. But you mentioned the ecosystem is fragmented, maybe a bit confusing.
It is definitely rapidly evolving and, yeah, a bit fragmented. There's a huge amount of activity, lots of new tools popping up. And importantly, there seem to be two main philosophical camps driving tool development.
Two philosophies, what are they?
The first is what you might call integrated augmentation. The idea here is to embed these agentic capabilities into the tools developers already use, their IDEs, their command line interfaces. It's about creating a kind of super-powered developer augmenting their existing workflow. The human is still central, but much more capable.
Okay, enhance the human. What's the other approach?
The second is standalone autonomy. This focuses on creating new self-contained platforms where the AI agent itself is the primary interface. The developer's role shifts more towards supervising the agent within this dedicated environment rather than doing the work directly in their traditional tools.
So augment the human versus let the AI do it and supervise. That's a fundamental difference.
It is, and the market is pursuing both paths right now. Choosing which approach fits best is a big strategic decision for engineering teams.
If developers want to build their own agents, are there foundational tools for that, like libraries or frameworks?
Oh, yes. For teams wanting to build custom agents, several open source frameworks have become really important. They handle a lot of the underlying plumbing, connecting to LLMs, managing memory, handling tool use, orchestrating steps. This lets developers focus more on the specific logic of their agent.
What are some of the key names people should know?
Well, LangChain was one of the earliest and is still very popular. It's incredibly versatile, modular, great for connecting lots of tools and data sources. Huge community support.
Okay.
For more complex stateful systems, especially with multiple agents collaborating, LangGraph, which builds on LangChain, uses a graph structure. It gives you finer control over the flow, better memory, error handling, even points for human intervention.
Sounds more robust for complex tasks.
It is. Then there's Crew AI, which is specifically designed for building collaborative multi-agent systems. It uses this nice crew abstraction that really feels like setting up a human team with different roles. Very focused on ease of use.
Interesting. Any others? Especially from bigger players.
Yeah, Microsoft AutoGen is an open source framework aimed more at enterprise needs. Good for conversational multi-agent systems, focuses on automation, scalability, and has features like sandboxed execution for safety. They even have a no-code GUI called AutoGen Studio.
Okay.
And Microsoft also has Semantic Kernel, which is a lighter-weight SDK available in .NET and Python. It's really focused on integrating LLMs with traditional code, emphasizing reusable components called skills and secure integration. Great for enterprises cautious about security.
So plenty of building blocks for custom agents. Now back to that integrated augmentation idea. How are existing developer tools changing? IDEs, CLIs.
Right. This is where we see AI being woven into the familiar environments. Two main categories are emerging here. First, AI-first IDEs. These aren't just traditional IDEs with a plugin. They're graphical code editors fundamentally redesigned with AI as a core feature. Cursor is a well-known one. It's a fork of VS Code, but deeply integrated with AI for conversational coding, debugging assistance, understanding, and refactoring the entire code base. Windsurf is another, focused on using project-wide context to help agents autonomously create features or complete tickets.
So visually rich, AI-centric environments. What about developers who prefer the command line?
They're not left out. There's a growing category of agentic CLI tools, minimal text-based interfaces for interacting with agents in the terminal.
Like what?
Aider is a popular open-source example. It acts like an AI pair programmer in your terminal, can work across multiple files in your codebase, interacts with Git. Claude Code from Anthropic is an enterprise-focused option, known for strong privacy and integrating with security workflows. OpenAI also has an experimental codex CLI.
So a choice there too. CLI for speed and control, maybe? IDE for visualization and managing big projects?
That's often the trade-off, yeah. Depends on the developer's preference and the task at hand.
Okay, now let's shift to the other philosophy, standalone autonomy. What about the bigger platforms, the ones aiming to be more like end-to-end AI software engineers?
Right. These are often larger-scale managed solutions. We're seeing major cloud and data platforms embedding agentic capabilities. AWS has strands for building agents deployed in their cloud. Databricks offers agent bricks for agents tailored to your specific organizational data. Dataiku focuses on governance and safety with its AI agents platform. Snowflake has a data science agent automating ML workflows.
So the big infrastructure players are getting involved.
Definitely. And maybe even more significant for widespread adoption is how existing popular developer platforms are adding powerful agentic modes. The prime example is GitHub Copilot's agent mode.
How is that different from regular Copilot?
Regular Copilot suggests code as you type. Agent mode takes it much further. You give it a high-level task, maybe point it to a GitHub issue. It then autonomously plans and executes the steps. Reads files, writes code, runs terminal commands to test, analyzes errors, iterates on a fix. All while keeping the developer in the loop for approval at key stages. It transforms Copilot from an assistant into an active collaborator.
That's a huge shift. And then there are the platforms that go even further, aiming for full autonomy. The AI software engineer platforms.
Yes, this is the bleeding edge. Devon AI from Cognition Labs made huge waves earlier this year by demonstrating an agent seemingly handling entire software projects autonomously from a single prompt, planning, coding, debugging, deploying.
Yeah, that caused quite a stir.
It did. While its real-world effectiveness is still debated, it definitely spurred a lot of activity. We now have open-source alternatives trying to replicate or build on that idea, like OpenDevin, Devika, AutoCodeover, and other commercial platforms like Zencoder and Codo AI are also building autonomous agents, often with a strong focus on code quality, testing, and security baked in.
It's a complex landscape. Those comparative tables and the sources you shared sound essential for navigating all these options.
They really are helpful, yeah. It's moving fast. V, the human agent team. Evolving roles and organizational structure.
Okay, this is absolutely critical. All this technology, these agents, it's not just about the tech itself. It's fundamentally changing the people side of software development, isn't it? Yeah. Team structures, developer roles.
You've hit the nail on the head. This is more than just a tool shift. It's a profound transformation of how engineering teams are structured and what developers actually do. As these autonomous agents take on more of the direct coding and execution work,
the human role changes. How?
The developer's primary function shifts. It moves away from being the author of every line of code towards becoming an architect of systems, an orchestrator of AI agents, and a critical validator of what the AI produces.
So less hands-on coding, more high-level oversight.
In a sense, yes. Think of it like the human moves from being in the middle of the workflow, doing the coding, debugging, testing tasks, to being at the top, providing the high-level goals, the strategic direction, the constraints, and giving the final sign-off.
Like managing a team of AI assistants.
That's a good way to put it. And this creates new responsibilities. The developer of tomorrow needs to be a skilled AI whisperer.
AI whisperer.
Yeah, someone who's really good at communicating effectively with these agents, defining clear goals, setting constraints, providing useful feedback so the agent performs well. It's a communication skill almost.
So what does their day-to-day look like then if they're not coding all day?
They'll likely spend more time on things like evaluating complex design or architectural options proposed by agents, rigorously verifying the correctness, security, performance, and maintainability of the AI-generated code. That validation piece is huge. And focusing on the really creative, novel problem-solving that's still beyond AI.
So what does this all mean? It sounds like the focus shifts decisively from implementation details to strategy, architecture, and quality assurance.
That's a perfect summary. Execution gets automated, judgment, architecture, and validation become paramount.
And this isn't necessarily about replacing humans entirely, is it? It's more about hybrid teams.
Exactly. The most effective models we're seeing emerge are hybrid human-AI teams. You might structure teams with specialized agents mirroring human roles, a requirements agent, architecture agent, developer agent, security agent, testing agent.
Like that crew idea from Crew AI.
Precisely. These agent crews collaborate, maybe coordinated by a human team lead or even a higher-level meta agent.
But the human touch remains essential for certain things, right? AI can't do everything.
Absolutely indispensable. Humans bring the deep business context, the nuanced ethical judgment, the strategic alignment, the subjective feel of user experience. An AI might propose an architecture, but a senior human architect makes the final call based on factors like long-term strategy or vendor relationships.
Or a human security expert reviews the threat model.
Right. Or a human product manager defines the overall roadmap. Human approval is the critical gatekeeper for high-risk actions, for handling weird edge cases, and for that final validation before anything goes live.
How do specific roles change, like a junior developer or a QA engineer?
We're seeing significant evolution there. A junior or mid-level developer who might have spent most of their time writing implementation code might evolve into a code validator and AI orchestrator. Their focus shifts to defining tasks for agents, reviewing and debugging the AI's output, managing the workflow.
So, different skills needed.
Definitely. And a QA engineer, instead of writing hundreds of manual test scripts, might become more of a test strategist and quality architect, designing the high-level testing strategy, ensuring the agent-generated tests provide adequate coverage, validating the really tricky scenarios. The responsibility shifts upwards.
This obviously means the skills developers need are changing too. Being good at leveraging AI becomes key.
Absolutely. And this could lead to what some are calling a barbell effect in skills demand.
A barbell effect.
Yeah, meaning high demand at both ends, but potentially less in the middle. So very high demand for those elite architects, systems thinkers, principal engineers who can design and govern these complex human agent systems.
The orchestrators.
Right. And potentially less demand, or at least a significant disruption, for the traditional mid-level developer whose primary role was task execution and writing boilerplate code, because agents will automate a lot of that. This hollowing out the middle could really change career paths.
So the ladder from junior to senior might look different.
It might. Getting good at coding might not be the only path, or even the main path anymore. We might need to cultivate architectural thinking, critical evaluation, systems thinking much earlier in a developer's career. We might see organizations with fewer mid-level implementers and more senior architects guiding agent teams.
So what are the absolute core skills needed to thrive in this agentic era?
I'd highlight 4. First, systems thinking, understanding and designing these complex, interconnected systems of humans, agents, and tools.
Okay.
Second, AI literacy and AI whispering, really understanding how these models work, their strengths, weaknesses, biases, and being able to effectively define goals, constraints, and feedback for them. Third, critical evaluation and validation, the ability to rigorously assess AI output. Is it correct? Secure, performant, maintainable. This becomes maybe the most important human skill.
And fourth.
Perhaps counterintuitively, foundational software engineering principles. They become more critical, not less. You need that deep understanding of data structures, algorithms, architecture, security to effectively guide, debug, and validate what the agents are doing. You can't effectively manage what you don't understand.
So strong fundamentals are still key, maybe even more so.
Absolutely. And organizations need to invest heavily in upskilling and reskilling. Training, sharing best practices, fostering a culture of continuous learning is going to be vital.
We touched on the productivity gains earlier, those impressive stats from Infosys and others.
Hmm.
Are there industry benchmarks emerging to measure this?
Yes, that's important for tracking progress objectively. The research community has developed benchmarks. SWE Bench is probably the most prominent one right now.
SWE Bench.
Yeah, it's a challenging set of real-world software engineering tasks taken from actual GitHub issues, and we're seeing agents get progressively better at it. Top agents like one from Refact.ai recently resolved something like 74% of the tasks on the main track. That shows real capability on complex, realistic problems.
That's solid progress. And what about enterprise adoption? Are companies actually putting serious money into this now?
The signs point strongly to yes. A recent PwC survey found something like 79% of companies surveyed were already adopting AI agents.
Wow, that's high.
And 2/3 of those were already reporting measurable value, mostly increased productivity. And maybe more telling, 88% of the executives said they plan to increase their AI budgets specifically because of agentic AI's potential.
So the investment is flowing.
It seems so. Analysts like Gartner are forecasting rapid growth too. They predict that by 2028, 1/3 of all enterprise software solutions will have agentic AI capabilities built in. That's up from less than 1% today. It points to a very fast, very significant investment cycle happening right now. Substance, risk, and the challenge of trust.
Okay, so the potential is huge. The tools are evolving rapidly. Companies are investing. But there's always a but, isn't there? Widespread adoption, especially in big companies with critical systems, depends heavily on tackling some serious risks. Trust, security, governance.
Absolutely.
Yeah.
This is the flip side of the coin. The very autonomy that makes agents so powerful also introduces new and complex challenges. We can't ignore them.
Let's start with trust. You mentioned earlier that software engineering is built on predictability, determinism. But AI, especially LLMs, are probabilistic. How does that square?
It doesn't square easily. That's the core conflict. Professional software engineering relies on systems behaving predictably, verifiably. LLM-powered agents are inherently non-deterministic. Give them the same input twice, you might not get the exact same output. This creates a fundamental trust deficit, especially in high-stakes environments like finance or healthcare.
And the black box nature doesn't help, right? Not knowing why the agent did what it did.
Exactly. It compounds the problem. If developers can't understand the reasoning behind an agent's decision or its generated code, it's very hard to trust it. Lack of transparency is a major barrier. Research actually shows developers are much more willing to trust AI output if the system provides clear justifications. Explainability builds trust.
So you made this point earlier. For 50 years, software engineering was about managing scale. Now, maybe the focus shifts.
I think it has to. Agentic AI promises to automate away a lot of the complexity of scale. So the central challenge for the next era isn't just scale, it's managing trust.
Programming with trust.
Programming with trust, the most critical human work becomes designing, verifying, and governing these autonomous systems so that we can have confidence in them, ideally, even more confidence than we have in purely human-driven processes.
And beyond trust, the autonomy and connectivity introduce new security risks, don't they?
Oh, definitely. A whole new class of vulnerabilities. First, there's simply an expanded attack surface. Agents need to talk to lots of systems, code repos, CI/CD pipelines, databases, third-party APIs.
Every connection is a potential weak point.
Exactly. The deep integration required for agents to be effective dramatically increases the number of potential entry points for attackers. Compromise one tool the agent uses, or find a flaw in how agents communicate, and you could potentially hijack the whole development process.
What other new risks emerge?
A big one is dependency chain opacity. Agents might autonomously pull in open source libraries to fulfill a task. A human might vet that library for security, check its maintenance status, and AI might just grab it based on functionality.
So you lose visibility into what's actually in your software supply chain.
Precisely. It makes traditional software composition analysis, SCA, much harder and riskier. You could unknowingly introduce malicious or vulnerable packages deep into your system. And then there's prompt injection and manipulation.
Tricking the AI through its input.
Exactly. Because agents rely on natural language prompts and external data, they can be vulnerable. A cleverly crafted prompt could trick an agent into performing harmful actions, or attackers could poison the data sources the agent relies on, subtly manipulating its behavior over time.
Okay, these risks are serious. It sounds like robust guardrails are absolutely essential, not just nice to have.
They are non-negotiable, a business imperative. These guardrails are comprehensive frameworks, policies, technical controls, monitoring to govern agent behavior and ensure safety, security, compliance.
There's a paradox here, isn't there? More autonomy requires more control.
It seems counterintuitive, but yes. To safely enable greater autonomy, you need a more sophisticated system of control. The more freedom an agent has, the stronger its constraints and oversight must be. This actually suggests something interesting.
What's that?
The winning agentic platforms in the enterprise might not be the ones with the smartest LLM, but the ones with the most comprehensive, configurable, and trustworthy governance and security frameworks. The engineering challenge shifts towards AI safety, reliability, control.
So what are the key pieces of an effective guardrail system?
Several components are critical. Granular access control is one. Strict role-based permissions, the principle of least privilege. Agents should only be able to access what they absolutely need.
Minimizes blast radius if something goes wrong.
Exactly. Comprehensive auditing and logging is another. Every single agent action, every human intervention or approval needs to be logged immutably. Essential for forensics, debugging, compliance.
Non-negotiable for regulated industries.
Absolutely. Then mandatory human-in-the-loop HITL workflows. For anything high-risk deploying to production, changing critical infrastructure, accessing sensitive data, human review, and explicit approval must be required. You need clear rules for when an agent acts alone versus when it needs sign-off.
The human is the final safety check.
Yes. And finally, robust data privacy and security controls. Ensuring any data the agent touches proprietary code, customer data is handled securely. Encryption, data loss prevention, DLP policies, the works.
So even with guardrails, there are still practical challenges in just getting these things to work reliably day to day, right?
Oh, definitely. Beyond security and governance, practical hurdles remain. One is still hallucinations and errors. LLMs aren't perfect. They can make mistakes, generate buggy code, invent things. Their non-determinism means occasional unpredictable output.
How do you mitigate that?
A key strategy is breaking large tasks into smaller chunks. It's easier for a human to review and validate smaller pieces of work, catching errors before they snowball.
Makes sense. What else?
There's the cost and complexity of implementation. Running these sophisticated agentic systems isn't cheap. It needs significant compute power, often GPUs. It needs access to powerful foundation models. And it needs specialized talent AI engineers, MLOps, systems engineers. It's not just plug and play.
Requires real investment and expertise.
It does. And finally, there's the risk of agent sprawl and technical debt. Without a clear strategy, organizations could end up with tons of different disconnected agents built by various teams, leading to chaos, redundancy, and a new kind of technical debt. You need a cohesive plan, maybe something like an agentic AI mesh architecture, to manage the landscape. 7. The road ahead, future directions, and conclusion.
So looking ahead, where's all this going? We've talked about the current state, the tools, the challenges. What's the future vision?
Well, while single agents are getting remarkably capable, the real frontier, as we touched on, is likely advanced multi-agent systems, MAS. The future vision isn't just one AI coder, it's collective intelligence.
Collective intelligence, like teams of specialized agents working together on big projects.
Exactly. Imagine dynamic coalitions forming. You might have a UI agent, a database agent, a performance tuning agent, a security hardening agent, a compliance agent, all collaborating, maybe negotiating, on a complex software system.
That sounds incredibly powerful. How would they coordinate?
Research is exploring different frameworks. You might have hierarchical structures where a manager or architect agent delegates tasks downwards. Or maybe more sophisticated debate-based frameworks where agents actually critique each other's work, propose alternatives, and refine solutions collaboratively, almost like a simulated design review.
Improving robustness through debate. That's fascinating.
It is. The idea is to leverage multiple perspectives to get a better outcome.
But for that to work at scale, across different tools and platforms, you absolutely need standardization, right? Otherwise, it's chaos.
You've hit the critical bottleneck. The lack of standardized communication protocols is a major barrier right now. The ecosystem is fragmented. Everyone's using proprietary methods. It's hard for an agent from System A to talk to a tool or agent in System B.
Like the early internet before TCP/IP and HTTP?
That's the perfect analogy. Those standards unlocked massive innovation by allowing seamless communication. We need something similar for agents.
Are there promising standards emerging?
Yes, there are efforts underway. The Model Context Protocol, MCP, from Anthropic, aims to standardize how agents get context from external tools, their external brain. Protocols like the Agent Network Protocol, ANP, and Agent-to-Agent, A2A, are focused specifically on enabling agents from different providers to communicate and collaborate.
What's the big implication if these standards take hold?
Well, this raises a really important question. Could this lead to an agentic internet, or an internet of agents? Just like HTTP created a network for information, these protocols could create a universal network for actions and services.
So an agent from my company could call a service or collaborate with an agent from your company seamlessly.
Potentially, yes, securely, via standard protocols. That would fundamentally reshape the software industry. Value might shift from building individual agents to orchestrating sophisticated services across this intelligent network.
That's a mind-bending possibility. So what's the ultimate goal here? Full autonomy. An AI that can take a business idea and just build a company.
That's the grand vision for some, yes. A fully autonomous AI software engineer, or maybe a team of them, that can take a high-level requirement, build an e-commerce site for custom sneakers, and manage the entire project, cradle to grave, with minimal human input.
Are we close to that?
We're making progress on automating specific tasks, but end-to-end project automation is still a long way off. It requires major breakthroughs in things like long-term planning and reasoning, maintaining context over very complex projects, and even better social intelligence for agent collaboration.
And crucially, you can't get there without solving trust, reliability, security first.
Absolutely not. Those are foundational. True autonomy is impossible without them.
So to wrap up, the history of software engineering was about managing the complexity of programming at scale.
Right. Building bigger and bigger, more intricate systems.
And agentic AI by automating a lot of that complexity.
Ushers in a fundamental shift. The central challenge for the next era, as we said, becomes programming with trust. The most critical human work shifts. It's less about implementation, more about designing, verifying, governing, and orchestrating the autonomous systems that do the implementation.
So the new frontier is really about creating the frameworks, the validation strategies, the guardrails, the ethical principles.
To confidently and safely delegate complex, creative work to AI, ensuring their actions stay reliable, secure, and align with what we actually want and value as humans.
Well, we've certainly taken a deep dive today into this incredible evolution of agentic AI in software development. We've covered its core ideas, its history, the huge impact on the SDLC, the tool landscape, the changing human roles.
And importantly, those critical challenges of trust, governance, and security that absolutely must be addressed.
It's clear this isn't just another incremental tool. It really is a paradigm shift, demanding new ways of thinking about how we create software.
Absolutely. It holds the promise of incredible speed and efficiency, but it also opens up a new frontier of risks that need careful management through those robust guardrails and ongoing human oversight.
So what does this all mean for you, the listener? Here's a final thought, something provocative to maybe chew on. Think about the software you use every single day. Your banking app, your streaming service, your social media feed.
Yeah.
How much of that digital world do you think, in the not-too-distant future, will be built, tested, deployed, and maybe even maintained by intelligent systems talking to each other, rather than primarily by human hands coding away? And what does that imply about the future of human creativity and control in this emerging age of autonomous agents?
Yeah, that's a big question to ponder. Thank you for joining us on this deep dive. Until next time, keep diving for those insights.